Okay, welcome back. So again, we're trying to graph a transform version of y equals cos x. We need some key points to start from. So back when you first did the graph of y equals cosine x, I asked you to look at the 5 key points that are on there. So again, the key points are the ones where the points are either at their maximum value, at the minimum value, or on the axis. So we have 5 of them here: 0, 1, 90 degrees, 0, 180 degrees, 0, negative 1, 270, 0, and 361. Okay, again, this is a graph you're going to need to know just as well as you would the basic parabola y equals x squared, and ditto with y equals sine x, which we'll look at in another example. Okay, so we're going to take these 5 points as points that are on the original parent function. Okay, so that will be these 5 right here. Okay, and then what we're going to do is, just like we did with quadratics, take these points, plug them into the mapping rule for x and y, respectively, okay, and calculate our image points. So for example, if I put 0 degrees in for x, 0 minus 40 is negative 40 degrees, and 1 in for y, negative 3 times 1 plus 7 gives you positive 4. So now we have a transform point at negative 40 degrees, 4. Okay, and you can repeat this process for all the other ones. So 90 minus 40 is 50, negative 3 times 0 plus 7 is 7, and then repeat for the other 3 points. Okay, so now what you have is 5 points that you can use to make a graph. Okay, and now once you make a Cartesian plane, you're now going to plot them. Okay, once you plot these points, you're going to connect them with a smooth sinusoidal curve. Okay, so your graph will look something like this. Okay, it depends on how nice you made your graph on graph paper or not. But again, once you connect your curve, it should look something like this. And you have your key points you can see right here. So there's negative 44, 57, 140, 10. Okay, so again, all you're going to be starting with is these 5 points right here. Okay, you make a nice smooth sinusoidal curve to connect them all. Okay, remember that this pattern will continue on forever in all directions, but again, what we've done is just graph one cycle of this graph. Okay, so with that in mind, let's try and get all this key information. So our amplitude, again, you might be able to see it from the graph itself. Okay, and if you look at your axis here, axis appears to be at y equals 7, so we can already answer that part right there, which means the amplitude is from 7 up to the maximum of 10 is 3. But again, you should be able to get that from the equation as well. So remember that our a value right here, ignoring the negative, is our amplitude, and our k value right here is the equation of our axis, y equals 7. Okay, so we can get our amplitude and our axis directly from the equation without having to look at the graph. Okay, as for the period of the parent function was 360 degrees. None of the transformations we did would change the period, so the period is going to remain 360 degrees. Okay, again, all the transformations we do in 3M, none of them will affect the period, so the period, with very rare exceptions, should be 360 degrees. Okay, I'll leave phase shift till later, because that's a new term we haven't looked at yet, but for our range, we know what our minimum and maximum values are. Okay, our minimum value is 4, you can see that from the graph. Our maximum value is 10, so our range will be any y value between 4 and 10. Okay, phase shift, again, it's a term that you may have seen in physics before if you've taken waves yet in that course, but if you haven't, that's okay. What phase shift is really talking about is how far the original function has been shifted horizontally. So with a sinusoidal function, phase shift is really just what we mean by horizontal shift. Okay, so in our case, we can look at our transformations, look at our equation. The x plus 40 means left 40 degrees. Okay, so our phase shift is just going to be left 40. Okay, so a lot went on there, but again, it's all process we've done before, right? Taking some key points off a parent function, throwing them into the mapping rule to get points to graph. Okay, so I'm going to have you try one on your own. Okay, this one you'll notice is a sine function instead of a cosine function, so you'll be using different key points to start with. Okay, remember, if you need a refresher, y equals sine x looks like this, and again, you can see some key points right here that you're going to be using from the parent function. Again, these are points you're going to need to know if you're going to be using a mapping rule to make transform graphs. Okay, so I'm going to want you to state the transformations, create a mapping rule, create a table of values like we did before so we can find the image points, so you can make your graph, and then again try and complete the table with all those features of the graph. Okay, so give that a try, either on your own or in a group, and pause it for now and push play when you're ready to go through it together. Okay, so let's just quickly run through this. So again, for your transformations, the negative gives us a reflection, the x-axis. The x minus 15 is what tells us we go right 15. Okay, the minus 9 tells us we go down 9 as a shift, and the 7 here tells us that we have a vertical stretch of factor 7. Okay, so we create our mapping rule. Our mapping rule is going to be x plus 15, negative 7y minus 9. And again, be careful with your key points you start with, because this is sine x instead of cosine x are going to be slightly different. Okay, so again, looking at sine x, it starts on its axis at 0, 0, then goes up, back down to the axis, back down to the minimum, and then back up to the axis. Okay, and again, they're all intervals at 90 degrees to start. So we take those points, plug them into our mapping rule. We should get these for our image points. Okay, so just check your math for all of them. We plot them onto a graph, so that would be these green points right here, and then we again connect them with a smooth sinusoidal curve. Try not to make it look, I mean, if you draw something like this, where it looks straight, okay, that's not good. That's not sinusoidal. Sinusoidal has curves involved. So again, try to make it look like a nice smooth sinusoidal curve. Okay, to get the key features, so the amplitude, again on the graph, you can see the axis is at y equals -9, okay, which means we have a distance to our maximum of 7, so we can get the amplitude and axis from there, or we can get them directly from our equation. Okay, amplitude is 7, axis is -9 from a and k respectively. Okay, the period, again, now the transformation we've done to change the period, so it'll stay 360 degrees. Our phase shift is our horizontal shift, which is right 15 degrees. And our range, our smallest value is -16, our highest value is -2, so our range will be any y value between -16 and -2. Okay, so if you follow this process to make a graph, it will work every single time. Okay, we just have to get used to working with mapping rules again, which some of us have forgotten because it's been maybe a couple units since we've done it. Okay, so just a couple other things to look at before we finish up this lesson. So now I'm going to give you information about a transformed sine or cosine function. It might be transformations, it might be a mapping rule, and I want you to just come up with the equation of the function. So I'd like you to think about these and try them on your own first, and when you've given them a shot, push play and we'll go through them together. Okay, so take a second to check your answers here. So again, we're looking at a transformation of y equals sine x here. So remember that our basic form is going to be y equals a times the sine of x minus h plus k. Okay, and again, if we can figure out what a, h, and k are, we have our transform function. So we're vertically compressed by a factor of 1/3. There's no mention of a reflection, so that means the a value stays positive, so that means a is equal to 1/3. Okay, we're translated right 5, so h will be 5, x minus 5 degrees, and then down 9 gives you a k of -9. So we get our overall function right there, f of x equals 1/3 sine bracket x minus 5 degrees minus 9. Okay, for b, we're working with cosine of x, so it's the same form that you're going to see up here, except it's going to be cos instead of sine. Okay, so again, from our map here, we can get an idea of our transformation. So x minus 8 means it's shifted left 8, which means h is negative. H is -8, sorry. Which means we have x minus -8, which is x plus 8 degrees. Our a value is going to be -2/7. This is multiplied by y in here. And our k is +4. So again, we get our transform function right there. Okay, so that's it. That's all. All that's really left in this unit, there's some practice there. But we're going to look at potentially a better way of graphing, or not necessarily better, but maybe a slightly faster way of graphing over the next little while, and work more with transformations of sinusoidal functions. Okay, so that's it. That's all.